Hello, my name is Alex Cohen, and I'm going to be talking about structure versus randomness for bilinear maps, or equivalence of three tensor ranks. This is all joint work with Guy Moshkowitz. So to begin, I want to review what a tensor is. So just as a matrix is an n by n grid of numbers, a tensor is an n by n by n grid of numbers. A complementary point of view that'll be useful for us is that a tensor is a trilinear form. So it's a function that takes in three vectors, x, y, and z, and it outputs a scalar in a trilinear way. The correspondence here is that a tensor is a polynomial in the vectors x, y, and z, and the coefficient of the xi times yj times zk term of that polynomial is the ijk entry of the tensor. Similarly, a tensor is also a bilinear map that takes in two vectors, x and y, and outputs another vector in a bilinear way. The coefficients of this output vector are each bilinear functions in x and y, and those bilinear functions correspond to the matrix slices of the tensor. So an example of a bilinear function is the matrix multiplication map, which takes in two matrices A and B, and it outputs the matrix A times B, the entries of which are bilinear functions in the entries of A and B. Okay, so before talking about tensor rank, let's talk for a moment about matrix rank. So there's many different ways to define the rank of a matrix, and they're all equivalent. There's a good reason for this, which is that any matrix can be put into the form where it has R ones in the diagonal and zeros everywhere else by changing basis on the left and the right by invertible matrices B and C. So no matter which way of defining rank, all these different ways of defining rank are measuring the same underlying quantity, which is the equivalence class of the matrix A up to change of basis. On the other hand, there are uncountably many non-equivalent tensors. So the story is just genuinely different for tensors. There's no one best notion of tensor rank. Instead, there are several competing notions that have different applications. And I just want to give a quick warning. The most common definition of tensor rank takes a value between 0 and n squared for an n by n tensor. And it's not what we're talking about. We're talking about a family of notions quite far from this one. Okay, so I just want to quickly overview the three notions of tensor rank we're going to be talking about before describing them in depth. So the slice rank is a combinatorial notion which was introduced by Tao in the context of the CAPSET problem. And it applies over any base field of coefficients. The geometric rank is a notion coming from algebraic geometry, which generalizes the codimension of the kernel definition of matrix rank. And this applies only over algebraically closed fields. And finally, the analytic rank comes from higher order Fourier analysis, and it measures the bias of the tensor T, which is viewed as a function of three vectors. And this analytic rank applies only over finite fields. So the main result, to spoil the show, is that these three distinct notions, which have all existed for quite a while, they've actually existed for more time than the dates I show here under different names. These three notions are all essentially equivalent. They're all different ways of measuring the same underlying quantity. And when I say equivalent, I mean equivalent up to linear factors, which for most purposes is genuinely the correct notion of equivalence for tensor ranks. Okay, so now I'm going to talk in depth about the notion of slice rank. So recall that a matrix has rank 1 if it's the outer product of two vectors. This is an example of a nice rank 1 matrix. Once we know what the rank 1 matrices are, we can define the rank of any matrix to be the minimal number R, so that's the sum of R rank 1 pieces. This is a very combinatorial way of defining the rank of a matrix. Analogously, we can say that a tensor has slice rank 1 if it's the outer product of a matrix and a vector. This is an example of a nice slice rank 1 tensor. Now we can define the slice rank of a tensor to be the minimal R, so that's the sum of R slice rank 1 pieces. An important caveat is that there's only one way to take the outer product of two vectors, but there's three different ways to take the outer product of a matrix and a vector, corresponding to the three different axes along which we can put the vector. And this distinction makes slice rank much more difficult to analyze than matrix rank, right? Because if you give me a tensor and ask me what the slice rank is, those three different flavors of slice rank 1 pieces are all tangled together, and it's very difficult to disentangle them. Okay, now I'm going to talk for a moment about geometric rank. So recall that given an n by n matrix, we get a linear map which maps from Fn to Fn. And the kernel of the matrix A is a set of vectors X which map to 0. This is a nice linear subspace of Fn. Once we have the kernel, we define the rank to be the codimension of the kernel. So the larger the kernel, the smaller the rank. Analogously, a tensor T gives a bilinear map, mapping from Fn times Fn to Fn, the coefficients of which are bilinear functions. We can define the kernel to be the set of pairs X and Y which map to 0. This is no longer a linear subspace, but instead is a curve variety in F to the 2n. So it's the vanishing set, not of linear equations, but of polynomial equations. In particular, it's the vanishing set of these n bilinear polynomials, which are degree 2 polynomials in the variables X and Y. So now that we have the kernel, we define the geometric rank of the tensor to be the codimension of this kernel variety. So to give an example, let the tensor T be the determinant tensor, which takes X, Y, and Z to the determinant of the matrix that has X, Y, and Z as columns. The bilinear map corresponding to this tensor is the cross product map, which takes X and Y to X cross Y. So the kernel of T is the set of pairs X and Y whose cross product is 0, which is exactly the set of pairs X and Y, which are scalar multiples of each other. This is a 4-dimensional space because we have 3 degrees of freedom with which to choose X, and then 1 more degree of freedom with which to choose Y. So the geometric rank is the ambient dimension, which is 6, minus the dimension of the kernel, 4. So the geometric rank is 2. On the other hand, one can prove the slice rank of this tensor is 3. So for this example, the geometric rank and the slice rank do not agree. Okay, now I'm just going to state some basic properties of the geometric rank. The first one is that it does not depend on the choice of axis. So in defining the kernel variety, I had to make a choice, which is which two input variables would be which two variables would be the inputs and which variable would be the output. Or in other words, which axis along which to slice the tensor. These 3 different ways of slicing the tensor lead to 3 genuinely different kernel varieties. But it turns out that these 3 genuinely different kernel varieties all have the same codimension. So the geometric rank is well defined in some way. It also turns out that the geometric rank and the slice rank both live in the range 0 to n, so they're at least comparable in that sense. And in fact, the geometric rank is bounded above by the slice rank, which is relatively easy to show. And finally, the geometric rank and the slice rank are distinct notions, as the previous example showed. There are tensors which the geometric rank is strictly smaller than the slice rank. So the first thing I want to talk about, which we proved, is that the slice rank is less than or equal to twice the geometric rank. Or in other words, the slice rank and geometric rank essentially measure the same underlying quantity. This is the first upper bound for slice rank in terms of geometric rank. And we're going to use this theorem as a tool in order to relate slice rank to analytic rank, which is the third notion of rank I'm going to talk about in a moment. Something important to note is that this theorem applies over algebraically closed fields. So what I mean by this is that if you give me a tensor over the finite field F5, in computing the geometric rank, I'm implicitly moving to the algebraic closure, which is because this notion of codimension really only behaves appropriately over algebraically closed fields. It doesn't work over finite fields. And so this theorem, in the proof, we constructively build a small slice rank decomposition, and we build it not over the base field F5, but over its algebraic closure. And I'll also just mention quickly that we have since extended this theorem to the correct analog for higher order tensors. Okay, now I'm going to talk about analytic rank. So here is an expression for the analytic rank of a tensor. Let's analyze it bit by bit. So first of all, x, y, and z are 3 vectors in f to the n. And t of x, y, z is a scalar in the finite field f. Okay, chi is a non-trivial additive character mapping from f to the complex unit circle. So for instance, if the finite field is fp, then the character chi takes the number x between 0 and p minus 1 to the corresponding root of unity. Now, its expected value over all possible input vectors is a measure of the bias of the output distribution of the function chi of t of x, y, z. Right, so in particular, these red dots sort of show the output values of the tensor t, and this expected value is going to be some element of the complex unit disk. And it turns out that for a trilinear function t, It's not just any number, but some real number between 0 and 1. So the closer that value is to 0, the more the output distribution behaves like random. And the closer it is to 1, the more it's biased towards the value 1. So that's why this expected value is called the bias of the tensor T. The analytic rank is then a function of the bias given by the negative log. So in particular, the analytic rank is small if the bias is large, and it's large if the bias is small, right? The closer the tensor is to behaving like random, the larger the analytic rank. So like a full analytic rank would be like n for an n by n by n tensor. So just like the geometric rank and the slice rank, the analytic rank also lives in the range from 0 to n. It's bounded above by the slice rank, just like geometric rank. It measures the bias of the function t. And this notion comes from additive combinatorics and higher order Fourier analysis. What I mean by this is that this notion of bias applies to other functions, not just trilinear functions. And we obtain the analytic rank by specializing the notion of bias to trilinear functions, to tensors. Okay, here is a lemma, which gives a formula for the analytic rank in terms of the kernel. So the way we read this is that this quantity here, the size of the kernel, is the number of f rational points in the kernel. So it's the number of pairs x and y with coefficients in the finite field f, which map to 0 under the bilinear map for t. So it's sort of just point counting the number of f rational points in the kernel. This log base f of the size of the kernel is some finite field analog of the dimension of the kernel. Right? To thesis, note that if the kernel were a linear subspace of the dimension d, because it's isomorphic to the linear space f to the d, it has exactly size of f to the d points. So this log is d, the dimension of the linear subspace. Right, so this is somehow a finite field analog of the dimension, and there's good algebrogeometric reasons to think of it this way. Then 2n is a dimension of the ambient space, so the analytic rank is like a finite field analog of the codimension of the kernel. And in fact, that was the initial motivation for defining geometric rank. Geometric rank was originally defined to be a sort of algebrogeometric or smooth version of the analytic rank. So we know that the analytic rank is always bounded above by the slice rank. So in other words, if a tensor is structured, then it must also be biased. A bound in the other direction, so a bound for slice rank in terms of analytic rank, fits the prototype of an inverse theorem in additive combinatorics. So the question is, given that a tensor T is biased, can we conclude that it has some structure? So the first theorem along these lines was given by Green and Tao. And they proved that indeed the partition rank, which is the right higher order analog of slice rank, is bounded by an Ackermann function of the analytic rank. So this is a terrible quantitative bound, but qualitatively it shows that if a tensor is biased, it must have some structure. Subsequent work extended the range of fields over which this applies. Harmony and Spielke later showed that slice rank is bounded by a constant times analytic rank to the 4th power. So it's a polynomial bound, which is quantitatively much better. Later work by Milosevich and Janzer extended this result to apply to partition rank. So it extended it to higher order tensors. But it's been conjectured by several authors that slice rank is not only bounded by a polynomial function of analytic rank, but is in fact bounded by a linear function of analytic rank. And this conjecture is saying that not only does it follow that from a tensor having bias that it must have some structure, but in fact that we can explain all of the bias of a tensor in terms of this particular kind of structure coming from slice rank. So the main result I want to talk about is that we proved this conjecture. We proved that in fact slice rank is bounded by 8.13 times analytic rank. I'll just mention that there's this issue of the fields we work over. This theorem takes place over the right field. So the slice rank composition that we make is over the field we started with. So this is the sharp inverse theorem for 3 tensors. We show that for 3 tensors, this notion of structure or slice rank and this notion of bias or analytic rank are really 2 sides of the same coin. The best bound prior to this work, as I mentioned, was slice rank is less than or equal to a constant times analytic rank to the 4th power. And the techniques we use are very different from the usual techniques for this problem. So the usual techniques are things like additive combinatorics, structure versus randomness decompositions, Fourier analysis, and instead we use algebraic geometry, derivatives, tangent spaces, and the local picture. I'll also mention that Adeprasito, Kashtan, and Ziegler independently proved the same result building on work of Schmidt. So there's some application of the theorem to the complexity of bilinear maps. So let F be a bilinear map, and let C star of F be the minimum number of multiplications needed to compute F within an arithmetic circuit. So it's in some way the arithmetic complexity of the bilinear map F. I'm going to let h infinity of f be the min entropy, which is some measure of the bias of the output distribution of f. So it follows from our theorem as an immediate corollary that if the min entropy is small, so the function is quite biased, then it can be computed with a small number of multiplications. This can be thought of as a quantitative version of Mahaney's theorem from theoretical computer science. So Mahaney's theorem says that if a Boolean function is very biased, then it can be computed in polynomial time. And what this theorem says is that if a bilinear map is biased, then it can be computed very quickly at a rate that's related to the bias. A second corollary is worst case to average case reduction for bilinear maps. So suppose that you have a bilinear map F, which agrees on average or for some substantial proportion of inputs with a bilinear map G, which we know has small slice rank. It follows from our theorem that you can compute F in a small number of multiplications, that F has a small slice rank as well. So this theorem it has a very different flavor from the slice rank versus analytic rank theorem, or it looks different, but it ends up being the same fundamental problem. It says that it's enough, in order to show that F is well structured, it's enough to show it's well structured on average. Okay, so now I just want to very briefly discuss the main ideas in the proof of the theorem. So suppose you have a tensor T over some finite field F, and you compute empirically that it has a large bias and small analytic rank. You want to then find a small slice rank decomposition. So the first step is to show that it has a small geometric rank over the algebraic closure, or that the kernel has a large dimension over the algebraic closure. The tool we use here is a Schwarzschild lemma, which says that if a variety has small dimension, then it has not too many F rational points. And this step is really where we use in a strong way that the tensor T is a polynomial function, not just any function. This is how we get started with algebraic geometry. So there's nothing really new we added here, but it is a very, very key step in the proof. Okay, now that we know the geometric rank is small, we constructively build a small slice rank decomposition. And the way we do this is by using a tangent space to the kernel. So we sort of use the data of the tangent space to the kernel in order to build a small slice rank decomposition of the tensor T. And then we've built from the information that the tensor T is biased, a small slice rank decomposition. Okay, there's one sort of issue with this plan, which is that the tensor we will have created will have slice rank decomposition not over the base field that we started with, but over its algebraic closure. To deal with this, we use a lemma of Dirksen coming from a totally different direction, which proves that in fact the slice rank of a tensor does not change too much when you go to the algebraic closure. So it sort of just fixes this field issue we were dealing with just for us. We don't need to think about field issues anymore. Okay, now I want to just sort of briefly overview the main ideas of this proof that slice rank is less than or equal to twice the geometric rank. So the idea is this. So say that T is a tensor, which has matrix slices A1 through AN, and let L be the linear subspace spanned by A1 through AN. We're going to sort of rearrange those matrix slices by taking a different basis for L. So if T has small geometric rank, then there must be some large subvariety of L consisting of small rank matrices. We're going to call this LR. So LR is going to be a subvariety of rank less than R matrices, and it's going to be an assumption that LR has large dimension. So what we're going to do is we're going to rewrite the slices of T by taking dimension of LR slices from the tangent space to LR. So sort of, in this example, these are like tangent vectors along LR, and codimension of LR slice is complementary. So this is sort of, we're going to think of T as being composed of a dominant term coming from the tangent space to LR and a remainder term coming from the complementary subspace. So just to begin with, the complementary subspace, which is this green part in the picture, must have slice rank less than or equal to the codimension. And the reason it just has codimension of LR slices, so you can build a slice rank decomposition for it with codimension of LR pieces just immediately. The really interesting part is that it turns out these slices come from the tangent space. No matter how big the variety LR is, those slices must in total have slice rank less than or equal to 2R, where R is the rank of the matrices. It has nothing to do with the dimension of LR. And one way to read for this is if the matrix we started with is the matrix with R1's the diagonal and zeros everywhere else, then every one of these tangent vector matrices, every one of these tangent matrices must have an n minus r by n minus r block of zeros in the bottom right corner. And then we can sort of build a slice rank 2R decomposition by taking first R pieces coming in the sort of x-axis, and then another R pieces coming from the y-axis. So at the end of the day, we use all 3 different flavors of slice rank 1 pieces, which is very important. We have to use all the 3 different flavors. And in total, this gives that the slice rank is bounded by twice the geometric rank as we desired. Okay, so I just want to briefly mention some subsequent work. So we've since extended this work to prove that the partition rank is bounded by a linear function of analytic rank, where partition rank is the right analog of slice rank to higher order tensors. So to higher tensor, right, this whole time we've been talking about order 3 tensors, but the sort of very interesting question is how this extends to higher order tensors. And so the key thing here is we bypass this use of Dirksen's lemma about the fields at the expense of a dependency of the field size on the analytic rank. So this theorem requires having a large field where the size of the field depends on the analytic rank of the tensor. So this theorem settles the structure versus randomness question for polynomials over large enough fields. Okay, that's it. Thank you so much.